So let's see. So just to recap, our goal was to talk about an exemplar application domain, and Dimitri suggested let's start with something simple like a dense matrix multiply, but even there the recursive decomposition leads to some interesting issues. And we could talk about different approaches to of how they could be handled, and we wanted to highlight the application domains, obstacles to automation, and other issues. Now, maybe the application domains part could be deferred, because that might to the later part of the meeting. That's my opinion, because that may that could end up being very broad. So we could just start with some concrete examples and then take it from there. I'll just present one slide in general terms, and then try to go around. I know that Dimitri, you have some slides too, right?
Yeah, if needed, I have some.
Yeah. So let me just find the right thing to share. Okay. So
it's working, Vivek. We can see you.
Okay. That's good. I'm just trying to get it to full screen, but yeah. So I think there are a few things that I would like to just lay out here to kick off discussion, and then, in fact, let me just mention all four, and we could discuss them before, and even before we get into concrete examples from specific frameworks. So one is how to express the code and data. So we know that the kind of form and code and data we want to eventually get to can be very complex to map to the complex systems that we're dealing with. And there may be ninja programmers or somewhere close to that who might, or even algorithm designers like Jim Demel's algorithm and all, who may want to think at that level. But there are many others who may want to just express the code and data as simply as possible, and by that I mean people are trained in trying to express computation data in a flat way. And there's been a lot of experience with different kinds of DSLs. And I just mentioned the polyhedral framework, because if you're talking about dense linear algebra, that's an example of something where you can start with an input that's very simple and flat, but look at code transformations and data transformations that can be very hierarchical and general for that simple input. So that's one point we can debate, whether we can get away with expressing code and data for mainstream folks in a flat way. The second is the space of data distribution. So I think hierarchical distributions are very important. I mean, this has been explored in a number of places, including the Sequoia and Legion projects at Stanford. In my group, we have the hierarchical place tree. But at the same time, for data distributions, in the HPC community, people have looked at data decomposition using things like block cyclic distribution, certainly for PGAS programming, combination of that. And for accelerators and GPUs, even for CPUs, there's been a lot of benefit in terms of exploring array of structure of arrays, differences in layouts. So if we take the approach that the input is expressed as simply as possible, then we can explore a space of data distribution. In my opinion, that all these different approaches for data layout and data distribution should be explored in a unified framework. And in fact, this can even be more general, and people have done some work where it could even include duplicate copies, for example, of some data elements, whether for halo regions or caching and so on. Exploring hierarchical decompositions of computation. This is pretty much like the kind of algorithmic approaches that like Jim Demel's paper took, but many others have been taking, you know, the cache oblivious algorithms and so on. But I think in some of the past work, certainly in the Silk past work, there wasn't a notion of mapping the decomposed tasks. And so if we have a notion of hierarchy, then we can actually, so I kind of see this as more like a spatial mapping, that your application can consist of large numbers of tasks that are created hierarchically, and you can pin them at different levels of a hierarchy. And the thing about a level of a hierarchy is if it's an intermediate level, there's still flexibility as to where it could execute anywhere in the subtree of that level. And finally, we need some affinity hints, because there could be a temporal dimension. There could be many things that could run at the same place, but there are few tasks that may be better off running simultaneously. It doesn't matter when they execute, so long as, you know, for example, producers and consumers in a streaming pattern and so on, so long as they're scheduled simultaneously. So first, I want to get reaction to this as a framework for discussion. What do people think? Are there dimensions, major dimensions that are missing from here? Are there things that are more important or less important?
Well, Vivek, this is Andrew. Just have a quick question. Maybe it's too detailed at this point, but in terms of implementation, so when you say express code and data as simply as possible, I hate to ask this, but does template metaprogramming include, is that included under simply as possible?
I see. So actually here I was thinking more on content rather than the language vehicle. So, and here I think maybe I was focusing more on flat versus hierarchical and simplicity. I kind of view something like template metaprogramming as an orthogonal linguistic issue. And I think relative to some of the complexities in hierarchy, I think it would be on the simple side, but you know, that's more a linguistic issue rather than the hierarchical aspect. Okay. Let me just make one other point. While I set that as a goal, just to put discussion, items 2, 3, and 4 in practice could all be controlled by the programmer as well. This is more like a vision where 2, 3, and 4 could be automated as much as possible, but they're definitely, I just want to mention, you know, programmatic opportunities for expert programmers to influence 2, 3, and 4. But yeah, go ahead, Andrew.
No, that was
that
you know,
okay.
You know, ultimately with, I think with template metaprogramming, one can, you know, realize some of these things, but you're right. I guess it's orthogonal to the actual goals. So,
right. Yeah, but the point is, can you express it? And because this is a high-hat discussion, I was focusing more on the hierarchy part. You know, so one question is, can we start with a flat specification and then come to the kind of hierarchies that we need?
So let me poke a little bit. Actually, if you here you said DSL, which again sounds like a linguistic interface rather than what it is that you're representing. So is in fact your focus here on what it is that you're representing and the kind of data structure? Yeah. Okay.
Yeah, I should have. Yeah, I think DSL was less of an emphasis. Actually, I wanted to. The point I was trying to make was it was less. It was more language agnostic. So
Yeah.
I just change it to procedural frameworks. I think that.
I think it is. That's an interesting or helpful distinction for us to make, just in support of that position of, if we're looking at a layered approach of what are the, if you will, the accidental features of the language expression and the language-based interfaces versus what it is that's represented and how underneath. That may be part of more of the infrastructure.
Yeah, certainly the integration of the two is very, very important for usability and success. But I think in terms of once we know the concepts we want, and then then it's more like a tactic. And in fact, there could be different domains where people pick different linguistic directions and integrate these ideas in different ways. In ways that are most natural to the underlying language framework.
Okay.
So, now at this point, I mean, I have tons of slides to talk about past work in my group along all these items, but I thought maybe at least it might be more interesting to go around a bit and hear from other people their approaches, and I can circle back to certainly my slides in more detail as needed. So, Dimitri, do you want to discuss sort of your viewpoint on this?
Yeah, I mean, I can start more or less any time, but would you like to mention something about specifically about this use case that we have now?
No, why don't you go ahead and then I will circle back, because I'm one of the things was I have a lot of content and I just didn't that way I can focus my comments after you share what you have.
Okay.
Okay, so I'll stop sharing.
Well, 1 second, I need to figure out. Okay. Sure.
Thanks, Dimitri. You got it.
Hey, can you see it?
Yep.
Okay.
Yep.
And if I go full screen, can you still see it?
Yes.
Okay. So I'll just probably start with very briefly about, again, what I'm doing is, so I'm building in a sense like hierarchical domain specific processor for hierarchical tensor algebra workloads, for like hierarchical numerical tensor algebra, which has applications in like different science domains, including like quantum chemistry and other things. But there's no really scientific specificity here. So the whole thing is based on this exatensor framework that I call it. So its goal to process hierarchical tensor algebra workloads, a kind of generalization of linear algebra. But it's based on an abstract layer which provides some basic primitives for hierarchical task scheduling within this context, though. And how it works, so there is some domain-specific data like tensors, and also there. So then this object, they need to provide method to be recursively decomposed. So they're stored essentially not as flat array of small blocks, but they're stored recursively. So each bigger tensor is a collection is a recursive collection of smaller tensors, and in such a way they are mapped to the entire HPC system, or like across the nodes or within the node, and then also the HPC system itself hierarchical view where it's recursively refined into smaller pieces, and then so the tasks are also recursively decomposed into smaller and smaller pieces, and those are pieces. Oh, sorry, there's some. And so those. I hear some echo.
Dimitri, we do not hear an echo, so
Okay. So those tasks are recursively mapped to corresponding parts of the HPC system. Like this is just general picture. So it's kind of fully hierarchical runtime where you have a hierarchical decomposition of the data, of the tasks, and of the HPC system itself. But then, going back to the specific case we just decided to discuss today, which I think is a very good case because of its simplicity, conceptual simplicity, but also it has some interesting consequences. I mean, interesting aspects to discuss probably. So for this specific case of dense matrix multiplication, and specifically for the recursive algorithm suggested by Jim Demel and others, which kind of delivers optimal bounds, communication bounds. So for this specific case, so this essentially I'll just pretty much show graphically how this is gonna work if I wanna run this case inside ExaTensor, which not necessarily it's a goal to run such cases, but this can be done, and I'll just show how that's gonna work. And there are throughout this there are two assumptions that so if you read the paper, so there are two overlapping of two steps, depth first and breadth first steps, and essentially the depth first steps they essentially create kind of a queue of tasks to be executed on the same computing unit, and in such a way this can also serve as in some sense over decomposition of the work in order to actually then this can be also leveraged to do the load balancing. This what is assumed and what is done in ExaTensor. And so at the top level we have dense matrix multiplication. That's, if you see on the slide, it's illustrated as the matrix equals some rectangular matrix times rectangular matrix, and on the right you see that this matrix multiplication is mapped, let's say, on 4 computing units, not necessarily homogeneous, so they can be of different architecture. And essentially, so first what ExaTensor does, it maps the data. When the data is created, it recursively maps the data, and so what happens is that it can map so the corresponding part of this matrices, as you can see now, this highlighted areas to the corresponding parts of the HPC system, and then the rest can map to the next part of the HPC system, and then repeat this recursively, go into smaller parts of the tensors and map them to smaller parts of the HPC system, and in such a way at some point stop when the granularity is small enough. I mean, essentially when you end up hitting each computing device, like each node, let's say. Then when we need to multiply matrices, so like the first task, so it creates tasks based on the existing data decomposition. For example, like the first task would be to compute this left part of the orange matrix, which is like a green matrix times blue matrix. And so as here we can see that one part is missing, so it's not local to the chosen part of the HPC system. So according to, like, let's say the Demel's algorithm, so like a replication prefetch will be initiated from the other part of the HPC system. Then on the next level of, and the other task is going to be also similar, but opposite way. Then on the next level of task decomposition, we'll get to smaller data pieces and smaller tasks, and also to smaller parts of the HPC system. But the whole idea is the same again. So now we'll have some replication prefetch within that first part of the HPC system itself. Then we'll have opposite way, and we already have some blocks, like here it's called temporary, which those blocks were already replicated at the previous stage. So they're no longer non-local, so they're local now. But we still need to do the replication on a smaller level. And this kind of recursive replication prefetch continues until the last level of this hierarchy, when actually all the tasks will be executed. So that's I think that's pretty much basic idea how this particular use case would run on a tensor.
So then, Dimitri, going back to how do you control the mapping of the data layout and the computation? Like, what things algorithmically do you have some approaches? Like, how do you specify what computation and what data should be co-located?
Yeah, right. So at this point, I'm not trying to achieve any absolute optimum of things. So since the main goal of ExaTensor is to process irregular tensors, meaning that they're not dense. So they're block sparse plus hierarchical. So there you cannot really assume any predefined regular pattern that you can efficiently exploit. At least I don't know how to do that. And consequently, I use kind of heuristical approach, and essentially the data is mapped in advance, and the tasks are then mapped not just randomly, but they're trying to be mapped to the places where with the maximal existing data presence, and the missing data is supplied as long as memory allows through this replication prefetch. And in this way, it's kind of a heuristic algorithm which is repeated at each level of hierarchy. So it not necessarily delivers the global optimum, but I expect it, let's say, I expect it to be reasonably well working for this particular, for the type of calculations that I plan to run.
Okay. So I'm happy to share some slides, but is there anyone else who wants to sort of share their approach too?
Maybe to queue up a point here, I think, Mauro, you had expressed some concerns about generalization of some of the things like Demel's algorithm for certain kinds of patterns, and how difficult it might be to make those dynamic. And I hear you saying, Dimitri, that you're taking more or less a static and predetermined data mapping approach, at least to start with. So as we look at some of these things, we may want to look at how they generalize and what the prospects are for a more dynamic handling case.
Yeah.
Yes, I mean, yeah, sure. We are going static, but that doesn't mean that we solve the problem. I mean, we are only partially kind of fixing it. If I have time later, I will share some of my points more specifically.
If you want to go ahead now for a few minutes, please feel free to go ahead, because I know in our group we worked on both static and dynamic mapping. So if you want to say a little bit about what you see as the challenges there, that'll be great.
Okay, I can go then.
So I think, Dimitri, you have to stop sharing. And then...
Yeah, I'm trying to do it now. Oh. Okay.
Sorry, quick question. Are these slides available somewhere?
The slides that all slides?
Yeah, yours, yeah.
Yeah, I think I'll upload them to the Modulata.
Okay, perfect. Thanks.
And I haven't looked here, but you had previously presented an exotensor here, so they may an earlier version of those may be available already, right?
Oh yeah, it is.
If you go to hihat.modulator.org and follow through to the presentations page, you'll have something to look at there.
Okay, thanks.
If you have, as per my earlier email to the presenters, if you want to upload anything else that's different there, that'd be great. And just link them into on the presentations page and then the minutes or whatever to what you post.
Yeah, I will upload my slides whenever I'm able to reset my password because I don't remember it. So.
I say same here. Yeah, the same problem.
But I will do it then. Can I go then? Do you see the screen? All right.
Yeah,
we do. Yes. So good.
Okay. So this come out from a conversation with CJ. It's more like a rant more than actually quantitative talk. I will try to put in the context of what we're doing, even though I'm not showing any specific thing on the software that we are working on. So what we want to achieve is performance portability in weather and climate code. So there are few users out there who are developing weather and climate codes, and they will benefit from having a common way of expressing their application needs without bothering too much with the low-level architectural details. And so what we want to achieve is to have a single source code for the weather model, for instance, and with source code we mean whatever the user needs to maintain. So we develop a lot of header-only libraries in C++ that is still technically part of the source code, but that doesn't have to be maintained by our user. Why weather and climate code? Well, it's because they use stencil computations, but there are a lot of complex dependencies. There are tens, hundreds of stencils per time step. Conditional executions of certain stencil will be executed if certain values are certain values or not. There is also the thing that there's kind of a limited number of Elo lines. So during this big time step, there's need also to perform communication. And when I mean communication here in terms of usual HPC system, so kind of MPI, Halo update operations. The stencils are reasonably big tasks, means that the domains are quite big, but in production runs they're not super big. For instance, in the latest GPU architectures, in production runs, we cannot fill a full GPU with one stencil. So there is opportunity for scheduling stencils in concurrently to try to fill up the resources. So the stencils are also data parallel computations. So it's not that we launch a stencil on a single thread. These stencils will run on multiple threads at the same time. And this gives some challenges when we want to generalize the expression of the application needs. And I will come later on this. One particularly, one specific rant I have is that from a developer point of view, task-oriented programming style usually suffer from the problem of the context switch overhead. So there's always some context switching involved when switching from one task to another task. And this, if you want, is not a big deal, but if you want to be performance portable, you need to have a way of managing your granularity in a way that is portable. But right now, I think it is not. You cannot, in a portable way, adjust your granularity very well. There were also discussion about how do we, so should we take a sequential code and try to make it into multitasking by splitting the computation? And this is usually, well, I mean, in general, it cannot be done, even if we know that, well, because we don't know if certain operation can be considered associative, for instance. So it's not easy to make these automatic splitting. Aggregation seems more applicable, so you start from small tasks and you try to fuse them as much as possible. If you could do it through inlining, that will basically will set the overhead to 0. Otherwise, you still have a function called overhead, which for very fine tasks it can be too high. And still, aggregation is not universally optimal. So if you consider, for instance, a parallel scan, if you coalesce the computations without taking into account the associativity of the operation that you are doing, you end up doing twice the work. So aggregation can be very useful in many cases, but still it might be suboptimal in a work from a work point of view. So the one of the most successful application then of these ideas is to express the finest granularity for the tasks, and then coarsening using basically inlining. Okay, there are also other approaches like the inspector execution, but still you have granularity issues at the higher level. So how much time do you spend inspecting instead of executing? So, and now I see this for, when I talk about expressing the finest granularity, I'm also talking about algorithmic motifs or patterns in which I express my computations, in some sense my DAG, using a keyword, passing my data, and then running my computation. In my point of view, the algorithmic patterns express the computation at the finest granularity, which basically gives you the splitting of the tasks, but it's not automatic. It is not automatic. It is coded. So the algorithm is a template that you fill up with your data, and you schedule your computation according to your DAG.
Can I ask a question?
Yeah, please. I'm getting too much abstract.
Maybe you're going to get to this, but one of the, could you just go back to the last one? One of the questions here is how much hope do you have for a templated expression of parallelism? And by that, I'm not referring in any way to C++ templates, wherein there is a description of the hierarchical structure that's expressed by the programmer that can be sort of unfolded down to the finest granularity if needed, but that doesn't a priori over decompose the problem and then expects things to be subsequently aggregated, nor does it initially under decompose it and require lots of dynamic and reactive further unfolding. How feasible is it to essentially be able to say, if the data is to be decomposed, perhaps in an AMR style, here's how it would be done, and then that set of possibilities can be handed to a dynamic runtime that can and scheduler and perhaps a hierarchical scheduler that can on demand do as much as is needed. I enjoy being able to see sort of, I expect that works in some cases, and for some algorithms and data structures, that's just not suitable. And is there good analysis of where that does and does not apply? And how does that fit with the particular cases that you're thinking of in terms of the weather and climate stuff?
Okay, yeah, I think that, so there was a project in Stanford, there was the Sequoia language, which were decoupling the description of the architecture and the description of the algorithm, and both were kind of described hierarchically. So then you could match, let's say, your algorithm to your architecture. I don't think there've been a lot of progress there. And I doubt it is universal. So that it works in all cases. But yeah, I really, I cannot really answer your question, I guess, in this case. In our approach, and I will come to it, we basically try to exploit every possible hardware resources hierarchically by basically encoding the algorithmic patterns so that one pattern will be implemented for a specific architecture. And when I need to move to another architecture, I will have the same pattern implemented in some other way, which gives also the problem that the number of patterns that we can support times the number of architectures, it tells you how many different versions we need to maintain in our libraries. So we cannot grow too much in the number of patterns, otherwise we end up in a explosion of versions to maintain. I don't know if this answered any of your points.
So, yeah, I'll just add to that I think, yeah, you're right about the Sequoia work. I think in our group, we've been able to work with both compilers, in my opinion, what we found is that compiler support also helps with the granularity issue, and then runtime helps with the mapping. And the two, that goes back to my point about expressing the computation as simply as possible, which means in a fine-grained way. So I don't know, was there anything more you want to present on this point, Mauro? Or I can, otherwise no. I can share something from my side.
Well, yeah, you could. I have a few other slides, but if you feel you have something else on this, then you go.
Okay, then why don't I take over then? And we'll post all our slides, of course, so people will have the full thing. So, okay, let me share. Second. So let's see if I can share. Okay. So first I want to let you know we had some work, compiler work, and I won't go through it in detail because I want to spend time on the runtime, where we would, so here's an example of a fine-grained OpenMP program, stencil computation, which is written conveniently for the programmer. It's got the dependencies. So I think, and we just use OpenMP notation over here because, you know, that's a standard. There are many other ways of specifying the same thing. So what it is you have the dependencies specified in a fine-grained way, but we've shown how you can take this as input and the compiler could generate coarse-grained tasks, both either which are dynamically scheduled, and I'm going to show you an example of that right now, or a little more statically scheduled. There's one construct in Duocross, called Duocross in OpenMP 4.5 that our group actually worked with IBM to contribute to the OpenMP standard. And while that may be convenient for the programmer, it's actually a very convenient for performance portability. You can let the programmer write this, what seems, so just to make clear, in case people aren't familiar with OpenMP, what this is doing is creating like n square tasks, one, you know, for each cell in a stencil, and specifying the dependencies according to the arrows on the left. And if you were to run it as is, it would run much slower than the sequential version because the overhead of creating the tasks and managing the dependencies would far exceed the little bit of work in processing the cell. But what we do with the compiler is that we use this parallelism to do loop transformations. In some sense, you know, you can encode your associativity rules where associativity does not hold in these task dependencies. And we can then generate coarser-grained code. So I just want to mention that. But now let me switch to the runtime part, and I'm happy to, so this was in a paper that was in PAC 2014. Let me just go to, so I think in an earlier presentation, and the slide should be there, but I'll add these as well. We've got this hierarchical place tree abstraction that first started because we were doing extensions to the work scheduling from MIT in different ways. And one of the extensions we felt was that was really critical is to be more locality aware. And so our abstraction of a hierarchy was basically, you could think of it like a tree of queues, except the queues need not be FIFO, like a tree of sets of tasks. And a task can have this async at where it says where in the tree it runs. And a policy, the current policy that we have is that the workers and the leaves, and the workers can be CPUs, GPUs, FPGAs, we've got examples of all of those, can execute tasks from any ancestor place. So what this means is that if you place a task further up on the in the tree, then it can run on more places. You're paying more attention to load balancing than locality. If you place it further down, it can run to a smaller set of places. If you place it at a leaf, it can only run there. So we found this convenient both for CPUs and for heterogeneous architectures. And I'm kind of switching between slides because now what I want to do is talk about 1 minute, let it go. This work that we had more recently, which was done in conjunction.
Just a quick clarification.
Yes. Yes.
Do you have a separation of semantics and performance tuning so that you can specify the semantics so that you know what to do, and then a tuner can come in and suggest where to put it in the hierarchical tree to be able to vary the performance without changing the semantics?
Absolutely. So the semantics is part of like the dependencies I showed you in the stencil code. That's an example of semantics, and that we want to have specified as simply as possible. And this hierarchical place tree is only for tuning.
Yep. Okay. Thanks.
Yeah. Now, it is a really obtuse programmer could choose to, if they wanted, just like somebody can write rank specific code or thread ID specific code in MPI OpenMP, somebody could try to do that. But the intent certainly for and the compiler generated code would make it complete the hierarchy part only for tuning. So now I just want to talk a little bit in the time that we have, is about some tuning work. This was done with Kathleen Nobe, whom I think many of you know has been working for a while on this concurrent collections model, and we worked with her as well. So the hierarchical place tree I showed you is on the right, but then we also have this, and this was my point 4 when we started the call, about temporal affinity, because hierarchical place tree tells you where things should run, but what this tuning tree or staging tree says when things should run together. So, you know, you can be, yeah, question? Okay.
I think we don't see the slide, actually.
Sorry?
I don't see any slide. I mean, I see your slide from the previous.
Oh, really? Do people see the slides saying CNC tuning execution model? No?
No.
Okay. Okay, let me exit out of the other part. Thanks for the...
I would like to point, while you are switching, I would like to point out a problem that like pragma-based approaches has, and then it comes when you want to integrate those computations that use these approaches and want to combine them at the same so you need to have some kind of global view of the resources of your system, and you need to place certain computation in a certain place and certain others in some other place. Plus, you need probably runtime systems interoperability in order to be able to run, for instance, HPX runtime over OpenMP runtimes, and this is super tough.
Right, these are. But we can have a longer discussion. Yes, there are challenges, but there are lots of groups working on ways to overcome these challenges. I think the fundamental challenges are coming from the new hardware directions, and that cannot be avoided. And I think there are ways to, yeah. Are you guys seeing the right slide? Yeah.
Yes. But just to cut in, we only have 3 minutes left, and I think John Biddiscombe had wanted to bring something up. I'm wondering if this is worth us continuing this conversation next month. It doesn't feel like we're necessarily going to finish talking about what we want to talk about here.
Yeah, I think let's continue. And I think there were some interesting points of view that, you know, Dimitri and Mauro brought up, and we could continue that and maybe try and do something online as well in our write-ups for the discussion. I think that would be good, because I did have detailed slides on, you know, dense linear algebra example using these hierarchical tree and the tuning tree, but we are not going to have time.
Sounds good. Can you guys both get me your slides, and I'll get them up on the site before next time, and we'll schedule to have the second half of the second half scheduled next month.
Okay. Yeah, that sounds good.
Cool. Did you want to finish up with anything, CJ?
Yeah, John, do you want to pipe up and?
Hello, everybody. It's John CSCS here. We, around about the May time frame, end of May probably, we're going to be having a workshop at CSCS, which is going to be a kind of CSCS, NVIDIA, and friends, targeting how we see the vision of some of these task-based frameworks interoperating with CUDA and the sort of future visions of CUDA. And I'd like to extend on the invitation out to the people listening today. I don't know most of you, although I know your names from reading papers and such like. But if there are people out there who'd be interested in joining CSCS and NVIDIA for a workshop, then please get in touch with me. I'll send an invitation to the Hi-Hat list and run it by CJ before I do so. But just to let you know that we're going to have a workshop in May sometime, and if you're interested, please let me know. Okay, CJ, I'm done.
Great. Yeah, thanks.
Thanks, Mario. And if I get that, I'll also send it out as part of one of the mail blasts, which might get a few more people than the mail list you can see.
And maybe just for a tad more context for that, I think one of the potential focuses on that was for looking at the layering potentially under C++ of, for example, HPX, hi-hat, and CUDA graphs and other things underneath. So it's a more general question of how do we poke down from some of these language standard interfaces down to infrastructure, and what would that look like? So that's one of the potential directions for the workshop, which is still in progress.
Excellent. Well, thanks, Vivek. That was great. I much appreciate it. And we'll post what we have up on the site, and we'll continue next month.
Yep.
And I posted notes there. If you, as presenters, want to go and just directly edit those to say more what you want to do or highlight some of the other key points, please do so. You have the rights to be able to do that.
Will do. Thank you. Look forward to next month.
Thanks, everyone. Thanks, Vivek.
Bye.
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 Thank you. And bye-bye.